So today we are going to first talk about in situ experiments in TM, then I will move on to the scanning electron microscopy experiments like in situ scanning electron microscopy and the electron backscatter diffraction, that is called EBST, those kind of advanced characterization tools used in the SEM. So let us first discuss about the in situ TM. We know that in situ experiments are very popular even from the very beginning of the transmission electron microscopy. When first time the high voltage electron microscope came up in 1960s, people started looking at the motions of dislocations inside the material. In fact, people started looking at the experiments on different kinds of solid state phase transformations in the materials while looking at in a high voltage microscope. But things have changed over the time scale. Nowadays we can even do in situ experiments inside a normal TEM. We don't need a high voltage electron microscope. The reason the high voltage electron microscopes were used in those days is because of the use of the thicker samples. Because we know that the behavior of a material in an electron transparent thin sample will be completely different than in a thick sample which we normally do experiments in the lab. So that's why to simulate the exact conditions people used to use thin foils or thicker foils, actually not thin foils, thicker foils inside the TEM columns and then study different kinds of dynamic behavior of the material by in response to heat or strain or deformation or even cooling. So because of that, different kinds of TEM sample holders were prepared. Sample holder which can do experiments during heating is basically consisting of a heater or consisting of furnace inside the holder, and then we can load the sample inside this holder and heat it up to see what is happening in the sample and record it in a video device. Similarly, sample can be cooled down using a cooling stage holder within the transmission electron microscopic column, and this cooling can be done using liquid nitrogen. So therefore, depending on the type of stimuli you want to use inside the holder, you can have different kind of holders. That adds up the cost of the microscopy because you need different kinds of holders. One can actually use the strain or the deformation also as one of the stimuli, so that you can indent a particular portion of the sample. You can strain even by applying a load, a tensile kind of loading, but most popular one for the in situ behavior of material during application of the load or stimuli like strain is the nano indentation inside TEM column. So we are going to discuss some of these experiments today. So dynamic behavior of material during a particular stimuli has become a very important because of advent of the nanocrystalline material. This is one kind of in situ experiment people do in the literature. Another kinds of in situ experiments which people do is the in situ growth. That is, suppose you want to grow indium phosphide nanocrystal, or you want to grow some semiconductor crystals inside a microscope column. So there are groups working in this world where microscope can be modified in such a way that one can deposit these crystals or the seeds of the crystal, and in the presence of the different kinds of vapor of the elements, how this crystal grow at the resolution of the electron microscope can be studied very easily using in situ microscopic techniques. And this has become very popular in different groups around the world, where one can actually look at different in situ experiments, different growth behavior of the materials at the resolution of this at the resolution of the electron microscope, and then infer information regarding the growth behavior of this material and correlate with the existing theories. So I cannot talk about all these things in this lecture because of the time constraint, but what I am going to do is I am going to show you some examples of those kind of experiments which can be done inside TEM column and obtain information during the experiments. Nowadays, with the advent of very good imaging devices like CCD cameras in the electron microscope, one can actually take video of the whole dynamic experiments in terms of digital imaging and then analyze this video later on to arrive at different kinds of conclusions from the experiments. So, compared to previous days where the videos were very what is called low resolutions, now even images can be obtained at the same resolution as the microscope provides us, and then analyze them to the best possible way. So, first of all, let me just tell you in a heating experiment. Normally heating experiment is done using heating holder. First thing you understand from this experiment is that TM remains same, only thing we are changing is the holder. So, if you have different sets of holder, one can run the same experiments, different kind of experiments actually inside any TM available in this world. You do not need to have a special setup for this TM. So, most importantly, in the high resolution microscope where the pole piece gap is very small, there normally people do not allow this kind of holders to be inserted in, because the holders are normally thicker. So, if the pole piece gap is small, then these holders may not be inserted properly and can create damage to the pole piece or any other detectors there present during heating or cooling or straining. So, therefore, normally the microscopes, conventional TEMs can be used except the high resolution configured microscope. In fact, there are reports that Titan can also be used for doing high in situ experiments. So, here I am showing such a holder which is basically provided by the company called Gatton Incorporation. This slide is basically because of the courtesy to Gatton Incorporations, and you can see that this holder has basically a simple specimen loading setup here, which can be seen in zoomed up view here, where there is a furnace around the specimen holding positions, and then this sample is basically inserted inside it, screwed down, and obviously one needs to use different kinds of spacer, so that sample during heating will not get welded and with the holder, and this holder can be cooled down using water inside this furnace, channeling the water through this furnace, and it can be tilted in a single tilt or double tilt mode. Both kinds of situations available, and depending the type of furnace is used, you can go up to maximum temperature up to some cases 1500 degrees Celsius. So, it allows us to heat a sample to different temperatures depending on our need. So, there, as I said, different kinds of holder available in this world. Other than Gatton, there are many other manufacturers which are preparing these holders. So, these are very generic. So, I am not going to go in detail of this holders type, but I will show you some experiments. This experiment, this particular one is taken from my own PhD thesis. So, I worked on iron germanium thin films, and as you can see if I deposit a thin films using physical vapor deposition like laser ablation here, the structure is basically amorphous. What can be obtained from this diffraction pattern is a very broad amorphous ring, and this corresponds to that these thin films are amorphous in nature. So, obviously one would like to know what will happen to the amorphous thin film when it is heated, or rather one would like to know the stability of the thin films. This can be done is easily in a heating holder, the one I have shown you. We just insert the sample inside the heating holder and then heat it up. As we heat it up from room temperature to about 473 K, that means 200 degrees Celsius, as we see there is a distinct change in the bright field micrograph. Correspondingly, electron microscope, the diffraction pattern gets a little bit modified, but not clearly seen, but there are black regions increasing in this micrograph as compared to the room temperature one. As you keep on heating from 470 to 573 K, there are visible changes happening, but most visible change takes place at 673 K, where you started seeing these black crystals where they are quite big. As you have to remember, this is 100 nanometer bar, so these crystals will be approximately about 20 to 30 nanometers. And similarly, the diffraction pattern got changing, you started seeing the spotty rings here, there, so you started seeing the crystals coming into picture. And as you heat alone at a temperature 773 K, that is approximately 500 degrees Celsius temperature, so you see this whole thin film has been crystallized, and the ring diffraction pattern shows the real nature. So therefore, if you want to do such a kind of experiments in the inside a TM column, you need to have to take the diffraction patterns at the end along with the bright field or dark field images. So once this thin film is fully crystallized at 773 K, it can be cooled down by switching off the furnace and then can be looked into the microscope again, and as you look into the microscope again, for the individual crystals which is formed like this ones, which are bigger one, we can actually obtain very nicely the micro diffraction patterns from these crystals and show they are indeed DO3 order. In this case, DO3 is a particular nomenclature used to depict kind of ordering presence, and in fact one can actually show that there are anti-phase domains inside the particles by doing these experiments. So what you understand from this experiment is that just by simply hitting a thin film inside a microscope column with a heating holder can provide us so much of information. Similarly, one can actually do routinely, this is again taken from routinely the heating and cooling experiments for the melting solidification study of the biphasic two-phase nanoparticles, which you routinely do during as a part of our own research activities. This is one I have shown you in the very first lecture of this course. What you see here is basically this two-phase nanoparticle present in the hard if image. This is basically a hard if image, high angle annular dark field image, and in the bright field image you can see that this is basically lead and this is a tin crystals in a one single particle. And obviously, as a material scientist, one would like to know how stable are these particles, whether there are any interaction between the lead and tin parts during heating or even during cooling also from the high temperature to low temperature. And as you know, lead tin melts about 183 degrees Celsius temperature, so therefore heating need not to be done at very high temperatures. So this can be done very easily in any heating holder, provided that heating holder can precisely determine the temperature. So this is this snapshot of pictures. What happens is again taken from our own work from our research group. If we align the particle in such a way that lead gets basically illuminated during dark field and tin is basically not oriented properly so that the dark field can be obtained, as you heat from room temperature to 90, 140, 137 to even 1 to 82 degrees Celsius temperature, as you see there is a change in the particle during heating. So from room temperature to 157 degrees Celsius temperature, there is not much change except the volume fraction of the lead and tin is getting changed. But as you heat it to 171 degrees Celsius temperature, whole particle become fully lead solutions, and then at 178 degrees Celsius temperature starts melts down, and finally at 182 degrees Celsius temperature it's getting molten fully. Therefore, this kind of particles which are embedded inside a matrix can be easily studied by in situ heating microscopy, and a lot of experimental informations results can be obtained. From there we can get information regarding stability of the particles and behavior of the particles during the heating at even microscopic resolution level. This provides us information regarding the the alloying at the nanoscale. So this is one such experiments which people do routinely nowadays inside a microscopic column. Another kind of stage, another kind of or other holder used in the real microscope experiment, in situ experiment, is called staining stage. This one is taken from Hycitron, thanks to them. So there is a holder where actually one can actually do nano indentation test inside the transmission electron column. What you see is basically the sample mounting stage, and this is the indenter at this position. So once we mount the sample inside this on this rod, and then this has to be electron transparent obviously, and then apply load to this indenter. Indenter will go and hit the sample, and then we can actually get information regarding the formation behavior of the sample. To show you one such again from our own work, if we take a silver nanoparticle and bring the indenter at the close to the particle, what are the changes happens? As you see, indenter is basically looking not like a SAT indenter at the microscopy level. This is, remember, this is 10 nanometer bar. So at this resolution level, this looks like a flat, a round rather, and as it come close to the particles, particle gets squeezed, as you see there, particle gets squeezed, and once the indenter is taken out, it leaves behind some permanent deformation in the silver nanoparticles. This is again can be done on anything, you can do on any kind of material, just putting inside the microscope column and then just deform it using the staining stage. So in short, I just wanted to show you in the last 10 minutes or so that what kinds of different experiments can be done using this what's called in situ studies. Well, obviously there are problems while doing the in situ experiments. In a transmission electron microscopic column, we cannot neglect the effect of electron during heating of the sample or during in fact phase transformation of the different phases during the experiments. That cannot be neglected. So therefore, there is always an effect of this electron beam, high energy electron beam affecting the behavior of the material during these in situ experiments. Then there are problems of the what's called the resolution, problems of viewing the material during the experiments. Many cases, some cases what happens while you are viewing the sample during the heating stage or cooling stage experiments, sample gets contaminated so much because of the material present around in the sample, we do not get any information at all. So these are the caveats you must remember once you are doing the experiments and once you are analyzing the experimental results from the in situ experiments. The next thing which we are going to discuss, or basically we are going to switch over from now onwards from TEM to the SEM characterization techniques, as I told you in the last class. So in the scanning electron microscope, which is routinely used by all kinds of users because of the easiness to use for characterizing the microstructure of the different kinds of samples, can be used for advanced characterization also. Nowadays scanning electron microscopes are available at a very high resolutions and also with a very high beam current also. Because of that, lot of experimental studies can be done which can provide us information regarding the sample behavior in the microscope in the real processing conditions. So EBSD is one such, but before I discuss EBSD, I would like to give you some idea about the scanning electron microscope because you might have forgotten from your basic characterization course. So to just next 5 minutes or so to just give you some basic idea about the scanning electron microscope, then I move on to the EBSD. So scanning electron microscope is basically very simple as compared to transmission electron microscope. It is a very simple microscope in the sense that number of lenses are small and the accelerating voltage is pretty low compared to 200 or 300 kilovolts. We are going to use probably 20 to 40 kilovolts, and not only that, the imaging is totally different as compared to transmission electron microscope here. So what you see here basically is electron gun source, which can be either a tungsten or lab 6 or FEG, the field emission gun, which is normally used nowadays, and then this is basically aligned or focused that are using a lens assembly. This is a condenser lenses, and then there is objective lens which actually focuses the lens the electron beam onto the sample, and then you can have a scanning coil here sitting which will allow you to raster the beam on the sample surface and then obtain the images at the same scan rate as the raster speed. And obviously this is a sample chamber in an scanning electron microscope, and there you can fit lot of things. As I discussed to you too, that when the electron beam falls on a sample, it interacts with the sample and generates all kinds of information from the sample, starting from the secondary electron beam to backscatter electron beam to the X-rays, or maybe other information like Auger electrons. Everything is possible to obtain. Depending on the type of detector used in scanning electron microscope, you can actually use these signals to obtain images, and these images can be further studied. So normally in a scanning electron microscopes, what you basically is nothing but a TV, as if you look at it. That is what I can say you. So there is a filament which gives electrons, and there is a sample on which falls, the electron falls, interacts with the sample, and obviously the electron beam can be focused by using electromagnets, which does nothing but a objective lens, and then after this interaction of the electrons with the sample, it generates signal. The signals can be then processed using different kind of detectors. Normally one can use secondary electron detectors or backscatter electron detectors for the normal imaging purposes, which are mounted here very near to the sample, or one can actually use X-rays to detect the different kind of elements present and quantify them. This is a very simple one as compared to the TM. As I showed you this slide I have showed you in the beginning of this of the discussion on the microscopic techniques. As the electron falls on the sample, it generates all kinds of signals. You can have a secondary electrons, or you can have a backscatter electrons, which is very standard. You can have X-rays, or you can have auxiliary electrons, or you can have a cathodoluminescence on the coming from the top surface of the sample. Only the electron is falling. On the other hand, if the electron passes through, it generates other kinds of signals which are not used for the SEM normally, which are this kind of signals are used in TM, which we have discussed. You can have elastic scatter electrons, inelastic scatter electron, or unscattered electrons, or many other things possible, which we have discussed in the terms of electron microscopy. So obviously, as you see, there are electron signal and photon signals coming from the samples, and in a scanning electron microscope, electron signal like secondary electron and backscatter electron beams or auxiliary electron beams, both these secondary and backscatter electron beams, they are used to image, or the X-rays, which are basically photons, they can be used for determining the element and elemental compositions also. Okay, so if once, therefore basically it's using the signal and plotting this signal on a TV screen. Just that's the SEM, scanning electron microscope. This is the conventional wisdom of any material scientist who ever used scanning electron microscopes, or they have seen a scanning electron microscope. But very rarely you will find people, or very rarely you will find the idea that scanning electron microscope can also be used to obtain crystallographic informations. Normally our basic understanding is that we can obtain all kind of crystallographic informations or diffraction contrast in a dimensional electron microscope, but in a scanning electron microscope also we can get lots of these informations, provided we know that how to obtain this information and how to use that. That is what has led to the discovery of electron backscatter diffraction. If you look back in the history, electron backscatter diffraction has come from channeling patterns, or channeling patterns which normally people have seen even long back. But only in 1990s, with the advent of computers and advent of the processing of this electron backscatter diffraction signals, we could see a rapid change in the study of the material using this technique. So many of these microscopes which you see nowadays fitted with the BSD detectors are actually come up in 1990s and later. Previously people used to do all some kinds of diffraction study in a scanning electron microscope, but they are very limited. So therefore, this is again I have shown it here, therefore how the backscatter electron comes into picture, because backscatter electron is very important for the BSD study. So as the electron falls, it just goes in the sample and generates secondary electrons, but it can actually get scattered and come out. Many times basically people say backscatter electron is same as which has been fallen on the sample and getting scattered back. That's why it is called backscatter electron in the scanning electron microscope. And these backscatter electrons actually having very high energy, more than actually 50 to even higher electron volts. So these backscatter electron can be then obtained, and as they say, they carry the channel the crystallographic information, which we will see right now. So first let me just go to the board and tell you what actually happens or what is unique. Unique to the backscatter image is the information related to the crystallographic nature of the sample. So origin of this contrast can be easily obtained from these two pictures. Let us suppose these dots, white dots, actually atoms in the crystal, and then electron beams are falling on the sample. In the first, the left hand side of this picture is to see, which I am just putting my hands on, where the electron beam is falling randomly. If the electron beam falls on randomly and gets scattered by the atom or nucleus, and then they can produce backscatter electrons. So if that is the case, then backscatter yield will be very high, because we are generating large number of backscatter electrons by this way. On the other hand, if suppose you have the sample or the crystal is oriented very nicely and electron beam is falling at along the symmetry, any of the symmetry direction of the crystal. Then what will happen in that case is that incident electrons will tend to channel between the lattice plane. That is what I have shown. You can see that between the lattice planes electron beams are channeling through these lattice planes, and this, because of this, the backscatter yield, electron yield will be very low, because all the electron beams are channeled through. Very less number of electron beams will be scattered and produce backscatter electrons. So therefore, although this is the physically what people think the reason or the origin of the channeling in a basically crystal. Now, so there is no way of confirming it or doing an experiment and see that. This is what the normal concept or idea we have. Now suppose if the angle of incidence actually of the electrons beam and the crystal can be varied at a from the random incidence to the along a particular direction, symmetry direction of the crystal, it can be varied. Then what will happen is that we can modulate the backscatter electron yield at different angles corresponding to the symmetry axis of the crystals. And if we do that, if we just vary this electron incident angle from these random to the symmetry directions, then we can actually modulate the electron intensity, the intensity of the backscatter electrons, or actually yield of the backscatter electrons, and get what is known as channeling patterns. And this is what I have shown you here. Let me show you one such pattern. You can clearly see that the channeling pattern looks like bands. Okay, they are actually bands like this, and then these bands actually meeting at certain points. This one is taken from pure iron crystals, which is taken from our own work, and these bands actually some cases meets like this. Those of you who have done conventional transmission electron microscopy, they are actually similar to the Kikuchi bands in the electron microscope. In fact, origin of these bands can be traced back to the Kikuchi nature. That is because of the inelastic scattering of the electron beams. Now, obviously, then if that is the case, then this can be related with lattice spacing, or basically we can get information regarding the crystal, the atomic spacing or lattice spacing. So angular width of this band is basically this one is approximately twice the appropriate bag angle for the given lattice spacing and the electron wavelength, so that accelerating voltage specimen can be reduced from the measure width after angular scale of the pattern is obtained. Most importantly, what you understand from the basic thing which I am showing you, I am going to discuss in detail about how these patterns are obtained and how this analysis is done. So from this is that this contains both the spatial and the angular information. Spatial information is basically nothing but the position of the crystal from where we are getting, or the microstructure from where we are getting these patterns, and angular information means from the crystal itself, how these bands are related to the orientation of the crystal. Both these informations are inbuilt within these patterns. So what I am going to do it in next 5-10 minutes time is that to show you how these are actually obtained, and then I will go back to the microscope. I will actually take you to the real microscope which we will have in our IIT Kanpur campus, and I will show you how these are obtained while doing an experiments, and then I will show you how this can be processed also. So first let me just show you some fundamentals inside the scanning electron microscope. So what is done in a normal scanning electron microscope is that the sample is basically tilted. The reason it is tilted to very high angle like 60-70 degrees is because the backscatter electron yield can be increased. The backscatter detector can be made to very close, and electrons which are generated coming out from the sample surface will be allowed, or will be going to the detector a much larger fraction, so backscatter electron can be increased. Normally we use fake or the columns like the fake guns like field emission guns in the transmission electron microscope, so that beam intensity is quite high. And the detector here is basically obviously phosphor skin, or we can use phosphor skin plus CCD camera, and these patterns which are called electron backscatter diffraction patterns or electron backscatter patterns, either EBSD patterns or EBSB patterns. So, they actually contain Kikuchi bands, as I told just now, or obviously they will be aligned in a certain zone axis pattern which I have shown you here, and they contain information regarding the orientation of the crystals with angular resolution of 0.5 degrees, and obviously there will be other effects like sampling cannot be done if the crystal size is less than about 50 nanometers, because then there will be overlapping of the informations, and there is obviously surface information. Surface sample preparation is very important, because if there is a oxide layer on the surface, we really do not get any information from the actual crystals, because beam will fall on this oxide layer and produce amorphous like pattern. That is nothing but useless thing in a EBSD. So, this is what is shown. You have a pole piece here. This is nothing but a pole piece of the objective lens, the sample which is tilted very high angle, approximately 70 degrees or more in this case, and then there is a camera with a CCD and phosphor screen sitting here, phosphor screen, and these backscatter electrons comes and fall on this, and it produces a channeling pattern like the one which is shown here. So, that is how we get information. Now, we have if you have a very large number of crystal in a sample, one can actually obtain this information from each point of the crystal and then process it. This is how actually experiments are done. But remember that the sample needs to be very clean, it is to be electropolished many cases to obtain oxide free surface layer, so that very good quality diffraction pattern can be obtained. Okay. How actually it works is very not very complex like many of the transmission electron techniques. So, you have a crystal oriented like this, what I am showing you silicon crystal here, okay, diamond cubic structure, and then if the electron beams falls like on the crystals, it falls on a particular plane or a set of planes rather, and scattering of the electron beam happens from like this, and the scattering of electron travels in all directions in a small volume, and electron that travel in directions that satisfies the Bragg's law, that is n lambda equal to 2d sin theta for a particular plane are channeled, and this actually leads to the formation of Kikuchi bands. Electrons hit the imaging phosphorus screen and produce a light, as we know. In a transmission electron microscopy also we use with the phosphorus screen on which the electron falls and creates the light. So, light can be detected by CCD camera, and then CCD camera can be used to convert this to image, and these patterns which are obtained routinely can then be indexed by knowing the crystal structure of the material, and then by knowing that we can obtain how each crystal is oriented in the sample. The real advantage of this kind of technique is compared to the TM is that here actually we can get information from very large crystals, large number of crystals in the microstructure, because SEM can allow us to see large number of crystals. This is just one such picture what I am showing you. This is, as we see, the different grains are mapped to different colors. Okay, this is how the data is visualized. This is taken from one of the HKL EBSD software manufacturing company in UK, the Oxford Instruments. We have the facility installed in our microscope is again Oxford Instruments. This is just for their routine data. So, what you see is that the grains are different color depending on the orientations. So, if once you obtain the orientation of the grains, and depending on the orientations of the grains, we can actually create a color map or grain orientation map, which is routinely done, and this provides us lots of information regarding the orientation of the grain boundary, type of defects presence, and many other things which we will discuss after we see the actual EBSD in the microscope next in the subsequent lectures.